Thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Manuel Rudolph from EPFL. He's going to tell us about Pauli propagation for classically simulating quantum circuits. So Manuel is a PhD candidate at EPFL in Lausanne in Switzerland under the group of Professor Zoe Holmes, focusing on the numerical simulation of quantum computing algorithms. So he's studying properties that make quantum circuits easy or hard to simulate classically, and how efficient classical simulability is connected to the barren plateau phenomenon. Manuel develops high-performance Pauli propagation software and is the main developer of the LOESA algorithm. And before his PhD, he worked as a quantum application scientist at Zapata Computing, developed hybrid algorithms utilizing classical and quantum computing resources. And recently, he was awarded the Google PhD Fellowship in Quantum Computing. And I guess very soon going to take up a doctoral researcher position at the Flatiron Institute in New York City with Miles Stoudemire. So Manuel, the floor is yours.
Yeah, thanks. So I hope to kind of spark a bit of a discussion here. Of course, I have a lot of slides. I probably have way too many, but the point I want to make here is I want to give you kind of a rough overview of this Pauli propagation simulation technique that we are, propagating, for lack of a better word, that we are proving guarantees for, that we want to kind of convince people is an actual simulation method they might want to use depending on what the setup is. Of course, it is not a simulation method that simulates everything. It will be worse than other methods in some cases. Also, our theoretical results, though sometimes they might seem pretty powerful and pretty strong, and sometimes they really are, they always come with caveats. So I'm going to do my best to highlight where you might expect, actual powerful simulation capabilities by this method, when in the end, if you want to simulate quantum systems, for example, it will be exponential. There's no way around it, for every interesting case, and that will always be the caveat going through this presentation. So I will probably skip a couple of slides here and there just to get through. But if anything is particularly interesting to you, I would prefer that we discuss it here, just because I'm not exactly sure what your personal interests are. Okay, so it might seem kind of silly, but I will start with how to even simulate a quantum computer, because not everyone is numerically minded, not everyone has a lot of experience there, and but everyone probably has a sense of the most naive way of doing it, which is with state vector simulation, right? So you can represent quantum states, pure quantum states, that is, as 2 to the n dimensional vectors, where n is the number of qubits here, right? And so every amplitude has complex coefficient, and operations you could either represent as, in the most general case, as 2 to the n by 2 to the n matrices, and then you do matrix vector multiplication. There are small extensions to this that make this much better than 2 to the n by 2 to the n unitaries. Like if your unitaries only act on a few qubits, you can do a lot more optimized operations. But there's no getting around the exponential scaling. So a different bunch of state vector simulators, they all have different library overheads, they have different implementation sophistication. But in the end, once you get above 15 plus qubits, everything is just going to be straight exponential, irrespective of what the library overhead is. And so you would think that the number of qubits is the ultimately limiting factor, but it is not. It is really not the number of qubits that's always going to be the limiting factor. It is the limiting factor for this method, right? But there are other methods, and this is kind of what a lot of people are not aware of. So I've been unfortunately involved in Reddit discussions on the quantum computing subreddit, and people were saying, "Oh, you can't simulate 80 qubits because that's or like you can't simulate over 100 qubits. That requires more computation time than the universe is old. And I'm like, no. This is in the worst case, like the most general quantum algorithm. Yes, it will be just straight exponential in the number of qubits. But this is not what we're mostly interested in. So, for example, tensor networks are a very popular example of a framework for simulation, for classical simulation that does not scale exponentially in the number of qubits natively, right? So they scale very favorably in the number of qubits, sometimes even linearly, if you deal with lowly entangled quantum state. Then there are also simulation methods which are based on kind of identifying a suitable basis for your computation. If the computation, like if your system has a lot of symmetry, you can work in that, and then it might just be polynomial runtime, although that's pretty rare. There's stabilizer simulation, which actually is not limited by entanglement, kind of like it seems to fill kind of this orthogonal counterpiece to tensor networks, but it's limited in something like magic, it's called, right? So the number of non-Clifford gates. So Clifford gates, we'll come to them in a second. They are free here, even if they're entangling, but non-Clifford gates are not free. And Pauli propagation actually is somewhat can be understood as like a subroutine of stabilizer simulation, but it has its own merit, and I think should be applied and should be viewed in very different contexts. But yeah, Pauli propagation is also not limited by entanglement. It's not limited by the number of qubits, but even kind of like even very simple seeming systems for like tensor networks, for example, could be very hard for Pauli propagation and vice versa. What exactly is hard for all these methods, we just really need to figure out. But in the end, either they are not exponential for simple cases, depending, or they probably are in some interesting limit. But it's just trade-off of different exponents. So what is the Pauli propagation algorithm? So what we're interested in right now, what we can compute right now, also with the library that I'm developing, is expectation values of observables, given some initial state, some quantum circuit with potentially parameterized quantum circuit. It doesn't have to be unitary, even though it says U. And yeah, so this is what we're computing. This is what we're estimating, let's say. And I've already written this in this way because we are actually working in the Heisenberg picture. So we're not forward propagating states, we're back propagating the measurement. So what's the intuition here in Schrödinger versus Heisenberg? And just to get a couple of fundamentals kind of like into your intuition, you're probably familiar with this concept of entanglement light cone, or like light cone, where if your measurement is some local Pauli operator, a lot of the final gates in a quantum circuit won't contribute at all, right? In the Heisenberg picture, this is natively like respected. If your Pauli like your measurement has like identities mostly, all the gates will just not do anything, right? It will natively kind of work in that sense. So local operators are like intuitively a lot easier in the Heisenberg picture. And if the operator is sparse in Pauli bases, for example, just like Pauli strings, Pauli observables, or Hamiltonians for energy estimation, and all you're interested in is expectation values, I would argue it's probably best to work with in the Heisenberg picture. I guess most people are not thinking about the Heisenberg picture. They just think we have to evolve states, even though it's completely symmetric. It's the same thing. So quantum circuit, completely arbitrary one, Clifford gates and Pauli rotations. Here it's a unitary quantum circuit. It's one that, if we start with a pure state, it remains a pure state. This is a universal kind of gate set. If you go, let M go to infinity, but technically we could put anything in here for the Pauli propagation framework. It doesn't really matter. All what matters is kind of how these gates act on Pauli operators. So for example, Clifford operations, how they act on Pauli operators, they give you another Pauli operator with some sign. If you for a Pauli gate, so a unitary that's generated by a Pauli string, either the Pauli that you're acting on commutes with the generator, then nothing happens, or they anti-commute, and then you get two Paulis, right? So let's say your O was one Pauli string, right? Then we act a Clifford gate, and we get another Pauli string. Then we act a Pauli rotation onto it, and we get If it commutes, for example, if your Pauli is identity, like on the side that you're currently acting the gate on, then you get the same Pauli back. If it anti-commutes, then it splits into two. So we really get this kind of like splitting kind of thing going on, as we see here, where if we start with a Pauli, we start splitting, and eventually we have to truncate. Kind of so we're propagating through a circuit, we have to start truncating because this will blow up. And this is, so for example, in tensor networks, a lot of the libraries have like default singular value truncations of like 10 to the minus 10, or like you set some maximum bond dimension, or you set some minimum coefficient threshold, and you truncate. And we need to do the same. Otherwise, you're instantly in the exponential kind of like is exponential scaling, even though maybe you have good reason to believe that most of the generated Paulis don't contribute that much. But yeah, you will have to generate, and there's different ways of doing it. We have a couple of default truncations, which will be mentioned today as well. What I kind of like hinted at here is this Pauli weight truncation. So if you get high weight Paulis, meaning a lot of non-identities, these tend to contribute less to expectation values. So this is already kind of also highlighting that expectation values are a lot simpler to compute or to estimate than just evolving operators, evolving states. Expectation values are a lot easier because you have one exponentially sized object, another exponentially sized object, and now you're taking the scalar product between them, the inner product, right? And inner products project out a lot of information. And so estimating expectation values is a lot simpler. And weight truncation, for example, is a truncation that can be very faithful for expectation values, but will make the full propagated object strong. But for expectation values, it might be very powerful. And so we kind of decompose this expectation value of the original operator that we kind of wrote up there into all of these backpropagated Paulis individually kind of overlap with the initial state. And all of them have their own coefficient, which are these like causes and signs and the actual plus minus, and then sums of them, because Paulis can also merge. If they're the same Pauli, we just add the coefficient, right? So we decompose this one big expectation value and in like potentially exponentially many small ones, right? But each of them is trivial to compute, but there's a lot of them now. So this is the Pauli propagation framework. We have some way to represent Paulis, and we have some way to act gates onto our Paulis. I mean, in the end, because of linearity of expectation values, the full expectation value can be exactly written as the sum of all the Pauli expectation values of the backpropagated Paulis, but we have to do some truncations to keep this feasible. Any question to this framework so far?
I just wanted to ask, so like you say that the U there doesn't have to be unitary.
Mm-hmm.
So how does it change if it wasn't?
So it doesn't change these rules at all. So really per gate, you can kind of think, what does a gate do? Like what does an operation do onto Paulis? For example, if it's like depolarizing noise, a Pauli, if it's not identity, we'll just get a prefactor here. So you have to kind of, if you think about it in its Pauli basis, like Pauli-like noise, so depolarizing, dephasing noise will just be like dampening all the Paulis. We'll be making them have a smaller coefficient. If you have something like amplitude damping noise, in the Schrödinger picture in computational basis, you think of pumping amplitude toward the zero state. In the adjoint picture, in the Pauli basis, you actually have Z Paulis that split into Z and I. So you have additional splitting induced by your noise, but identity Paulis, but like low weight Paulis are out there, fewer of them, and they also have smaller coefficient because of depending on the noise rate. So there's a lot of arguments of like when these still remain efficient to simulate, but all you have to basically define is your rule of how a gate acts on Paulis. This is also how we design our software. And as long as that is defined, you can just like put it in the circuit and run the algorithm. So it will just create more splitting and change the coefficients. But all of this entire setup doesn't change at all. It only matters how these these needs to be defined, and then you're good to run.
Yeah, I see. Thank you.
Yeah, thanks for the question. Okay, so as I already hinted, noise makes quantum computer simulable in general, let's say, right? I would maybe, now that I'm giving this talk, I will put a different nuance onto it, which is like, if noise doesn't destroy the quantum computation, probably the quantum computation is also simulable with noise. Yeah. So just like a very brief rundown. So there was the seminal paper by Aronov, Jungao, and others that random circuit sampling, which is this kind of like this like Google quantum supremacy kind of like a workhorse, is actually simulable in polynomial time for fixed error rates, right? And they actually use a simulation method that's, at the time it wasn't like bundled as this, but it was Pauli propagation, right? With and all the error model was depolarizing noise, and with depolarizing noise, you have all of your Pauli paths being damped, and so the deeper you go, you actually can show that the higher Pauli weight Pauli has, the more it will be damped, and then you can actually sample, which is a really hard task in general. You can sample by neglecting all of the global correlations because they are most damped by exponentially damped by the noise, and you can sample from your Pauli paths actually and produce computational basis samples. And but for constant noise, right? This is always kind of the thing. Then so this is how I got involved into this topic last year, working with Enrico and Christina mainly, that expectation values of variation quantum circuits, like in general, but for landscape, can be simulated with arbitrary Pauli noise if it's constant strength. So not just dephasing, not just polarized, not just dephasing. Like if you have any Pauli noise and your circuit is right, given our noise model, of course, there's always a caveat. You have polynomial runtime for fixed additive precision, and we're also continuing going down this direction with, for example, Armando. He's a postdoc at our group now, and we're also, we're ongoing collaborations here. We're just showing that more and more kind of like noise model lead to efficient classical simulation in certain settings. But yeah, I mean, this is, I guess, not shocking that noise makes things easier to simulate. But there are caveats here already, which is usually there's a certain amount of randomness that goes into proving this, like either like over like a certain maybe averaging over your angles, or you're averaging over input states. But for like specific instances, for example, if you did like noisy quantum simulation, it's not clear that this would be polynomial runtime, even with all of these kind of approaches. I guess if you actually have depolarizing noise, like the strictly depolarizing noise, you probably can get worst case errors, but not in general. Yeah, not going to go into our work this much, but basically in this noise model, the more a Pauli split into more paths, the more noise it would accumulate, and we can bound the error we get and the truncation error we get by truncating after a certain number of splits in a Pauli path. But yeah, it's average error. It's exponential in the kind of in the cleanliness of your right, and 1 over the noise, and uncorrelated angles, which kind of goes to the average error kind of segments. So if you did noisy quantum simulation, this bound wouldn't hold. So what about even noise-free? And you will see why. So what about noise-free stuff, right? Let's say like QML, variational quantum algorithms. Surely this would be better, probably not. And right, so you could try to plug variational quantum circuits, parameterized quantum circuits into a lot of things, but there is this very kind of infamous phenomenon by now, which is barren plateaus, where you have exponentially small gradients or like variation on your landscape. And this is not bad because it's slow. This is bad because you need high precision to tell apart, like differences. And on a quantum computer, high precision is very expensive to come by. So it's not about being slow. It's about not drowning in shot noise. right? So this is also something that people often don't appreciate, how bad barren plateaus really are on quantum computers. They're already classically bad if you classically simulate, but they are especially bad on quantum computers. And for every measurement tells you very little. So there are ways that people have tried to fix this, but we showed last year in a really cool kind of collaboration led by Marco at Lionel that we hint towards the fact, and we argue for the fact, that if you can prove that you don't have barren plateaus, you actually make your quantum circuit simulable. And so what's the, right? So because if you can prove that something's barren plateau free, you're actually saying it must live in an identifiable polynomial subspace, because barren plateaus are kind of diagnosed by exponentially decaying kind of like gradients. And if we know the polynomial subspace, we can use that subspace as a basis for a computation. And so this can, right? And so basically it seems like either we have a model that just that's classically simulable, but technically it's not impossible that it would work on a quantum computer, or it's not necessarily classically simulable, but we also don't know how to make it work on a quantum computer. So there seems to be this ongoing kind of like dichotomy where either we know that it will work on a quantum computer, like on current quantum computers, or like we have a good reason to suspect that it will work, like it's shallow enough, and like it's that there's not so much or maybe it's you don't have barren plateaus if you're in a variational setting, but then probably it's classically simulable. And the only examples I know of that don't fall into this kind of like tension that we see here is Shor's, like discrete log problems, but we can't make them work without error correction. So that's kind of out the window. And then there's quantum simulation. Quantum simulation, so like real-time dynamics of quantum systems, seems to be properly hard, classically, even with noise, with some amount of noise. It's probably still technically exponentially hard quantumly, but if you just reduce your error rate by like some reasonable amounts, you can tune the exponent so much that it's completely out of range classically. So this is kind of what I'm seeing. Right? And so what's the intuition behind this absence of barren plateaus? Well, so barren plateaus are exponentially vanishing overlaps. So if you just randomly initialize your model and you have some measurement, again, it's two vectors in a Hilbert space, and if something's random, they're just going to have exponentially small overlap with high probability, they're going to have exponentially small inner product. Two random vectors in an exponential space. If you don't have that, then there's two possibilities. Either you're restricting yourself to drawing random vectors from a polynomial subspace, then you don't have exponentially small overlap, or you are pre-aligned with the solution. And we don't know how to do that, right? So our group is trying to understand how close you have to be to the solution to have some substantial gradients even in an exponential full subspace. It's not clear how it's not clear how good of a pre-alignment you need to make variational algorithms like this work. Just like to highlight, even if some models could technically kind of have technically fill some exponential full space, if most like randomly drawn models live in a polynomial subspace, then it's still, for all intents and purposes, like effectively classically simulable with different methods, and a lot of them are also polypropagation. One way we showed this is for quantum convolutional neural networks, where they have been touted as this very interesting, promising model that doesn't have barren plateaus, like generically. And it's like, okay, that's cool. But we basically show that yes, they work well because they are usually trained, like they're usually applied to easy data sets, and when they work on those data sets, we can just simulate them classically. And so the way we did this is by simulating QCNNs with with low Pauli weight truncated Pauli propagation. And we trained our classically truncated, like model. And we scaled it to bigger problem sizes that people that have faithfully simulated QCNNs, and we got better accuracies. So it's like, it seems like basically, yes, these models have nice properties comparatively to other quantum models, right? But they're just still worse than we don't know when you would want to use them, because we suspect for cases that aren't classically simulable, QCNNs are also tend to be bad. We don't know how to make them work for hard problems. So kind of if the QCNN is successful, you probably have an easy data set, which means you could probably just take, even for quantum measurement, like for quantum data, classical data, just forget it. For quantum data, you could just take in measurements of the initial state and then do all the training of the QCNN classically. Yeah, so, technically there is the option, because the QCNN is more expressive in some exponential tails than the classical simulation, that maybe you either need to converge to that, or you can kind of converge through it, have like better behavior. But because our simulations classically, like up to like 1024 qubits, was just better than faithful simulation, we just don't see the evidence that this is what's required of QCNNs. But basically we need people to think about not generically out of the box models, but like much more tailored models. So this Louisa algorithm that has been mentioned a couple of times is kind of a personal twist of mine, which kind of falls into the classical surrogate kind of like domain, which has different definitions depending on who you ask. But basically, the difference to just traditional Pauli propagation, with traditional already is like not in everyone's minds, but let's say traditional Pauli propagation, instead of just backpropagating the operator and overlapping it with the initial state, what we could do, because the initial it's expectation values, what we could do is we could do this first propagation, keep track of all the paths and all the merging and all the splitting, and then probably only very few, it would probably mean, yes, very few of the final Paulis would actually contribute meaningfully to the initial state. And so you could kind of just reevaluate in this kind of light cone intersection between the two methods, right? And this has an initial overhead of like, you have to build a graph that represents all of this, and this is complicated. And the code I have, like works for certain setups, but it's not as like general as I would like it, but we're working on it. But every reevaluation is just so much faster. And so what you could do is you could measure, like classical shadows, kind of, or like anything from a initial state, if you even need a quantum computer, right? But if you don't need the quantum computer, just forget the step. You compute expectation values with low weight Paulis. What we did for this QCNN, we kind of like selected the ones that had the highest variance across the data set. Because if you have low variance across the data set, then this doesn't contribute to your classification, right? The only thing that would contribute to classification problem is if you had like high variance between your data points. So we selected a very small number of like Pauli expectation values, and we only trained kind of like along this like very sparse subgraph of the full propagation. It's a super truncated model, but it just works much better, right? And kind of in absence of the QCNN, this would still be something that you could do, where you do this initial heavy load, you realize, oh, only a very small subset of final Paulis actually contributes. And for really fast reevaluation, you could use this kind of like surrogate approach. And I think for VQAs, this is probably just good. But, it's just the flavor of Pauli propagation that we're putting on top. Okay, and so also recently, so this summer, with our postdoc Armando, and so in the group of Zoe Holmes, with collaborators Robert Huang, of course, Marco Cerezo from Lanel, and Alex Schmidhuber or Sasha, this was a really fun collaboration as well, where we showed was that if you do low weight Pauli propagation, so you chop off like high weights, and when I say low, I mean like any, like constant number. It could be hard, it could be like hard, right? As in like challenging, but just a constant high, like a constant cutoff is sufficient on average over like uniformly sampled circuits, but not, they don't need to be fully random circuits. It could be, so pick the ansatz, whatever ansatz you want, as long as it satisfies some, like you have to have something like two orthogonal single qubit Pauli rotations per qubit, like every now and then, right? Like this is not the biggest caveat. The biggest caveat is that on that ansatz, you randomly draw parameters, and on average over all of your randomly drawn parameters, you will make a truncation error that decays exponentially in the truncation threshold. Now the simulation becomes exponentially harder in the threshold, right? But what that means is for every constant error on average that you want to make, you can find a truncation value when you're guaranteed that your average error is lower than the error you want. Every particular parameterization could still be more wrong than that, right? But if you just draw a random parameterization, it is very unlikely to be significantly more wrong than that. You can find angles. Like, for example, in every circuit you can design, there's probably some sub-circuit that would correspond to evolving a quantum system if you correlate all the angles in a certain way, so that would kind of like be like a trotterization of some Hamiltonian. That's a correlated angle, and that's a subset of the uncorrelated angle one. Those probably are the ones that have the highest error, as far as we can tell. But if you don't pathologically attack kind of this like the circuit generation, this will be still very representative of the average error. So it seems like expectation values for generic quantum circuits are on average not exponentially hard to approximate. Like, there's a lot of words, but this is what we find. So you would think, oh, quantum, like the average quantum state is exponentially hard to simulate. That's probably true. But not expectation values of the average state. So of course, if you have fully random states, just guess 0 for expectation value, or like guess the trace of your operator, and it's probably correct, right? For very shallow circuits, you can just strongly simulate it, right? You can do it. What we are kind of like saying is that even in its intermediate regime, where you interpolate between the very shallow and very deep, it's still at no point on average exponentially hard. But of course, you need the so-called locally scrambling ansatz, which, for example, is fulfilled if you have like Rx, Ry on like any qubit. It was actually also satisfied by the QCNN, like by the generic implementations of them. But yeah, the biggest caveat is it's uncorrelated angles, where like randomish parameters. But this basically means at circuit initialization, if you were interested in VQA, QML kind of stuff, you're simulable. Or you have barren plateaus. So depending on how you see this is either a very strong result or a very weak one. It's very strong in that it is like this seems like that hard, like, a random quantum circuit is not hard to simulate expectation values with. But on the other hand, who cares about generic quantum circuits? So, depending on how you stand on this, you see this as a very strong or very, irrelevant result. It's probably something in the middle. Right? So the task really becomes design the quantum circuits that are really interesting to you, figure out if they're classically easy or not, right? And then you will be happy either way. What we're currently doing is just applying quantum to whatever. And generically, it either doesn't work quantumly or it also works classically. So I think we should really get away from this. What we really need is find setups to solve problems we're interested in, and then figure out if we need a quantum computer for them. Right? It's kind of the obvious thing a lot of people were already saying. I'm just kind of restating this here. For this paper, we did some 8x8 kind of like 2D circuit simulation that a paper in PRL said wasn't classically simulable, and we show that with every individual Pauli truncation order, we get an average error that roughly decays exponentially, and our error bounds are trivially satisfied. We actually do way better than the error bounds. And the simulation time goes exponentially, but this is on the scale of seconds, and this is my laptop, so and a single thread. So this is not right. There's a lot to gain here on the classical performance side. And okay, so this is not garbage code, but you can parallelize and everything. So what is this plot saying? That in this circuit, it's actually kind of pathologically designed in the way that it creates exponentially many Pauli operators very quickly. But they are almost all super global on the 64-qubit problem. And this inset, we are showing kind of this number here times the expected overlap of each of these operators with the zero state, for example. And even though we mostly create global Paulis, the actual contribution, the cumulative contribution, actually still decays exponentially in weight for the setup, right? So this is how we get. This is the difference between simulating faithfully a quantum state or like some evolution of an operator, because this is terrible to simulate. There's exponentially many Paulis in this bulk, right? But for expectation values, we can mostly ignore them all. Especially for like uncorrelated parameters, you probably lack something that a different part of the physics community calls operator flowback. So you don't have the, or like backflow. So you don't have this backflow from high weight to low weight Paulis. If this did happen in a correlated manner, truncating them away would be wrong, right? Like you would get wrong outcomes. But if they just tend to become more and more and more and more high weight, then typical expectation values, and actually even for physics simulations, I don't see anything different. Only the local ones matter, and so you can, it's okay, it's faithful. Now, if only the local ones matter at the end, but you have systematic backflow from high weight to low weight, this truncation needs to be set sufficiently high to allow for the backflow for this expectation value not to be systematically wrong. But yeah, this needs to be quantified. Like we don't have any, I don't think there exists like actual solid theory on this. This is physical understanding plus like numerical understanding. But we show even with correlated angles, we still get some improvements here in kind of like error. So it's always beneficial to do it compared to not doing it. The question is how high do you need to set the threshold, and is that too much for you practically? So that's what it boils down to. And just kind of how I got into this a bit more. How I got into this was actually, so after after proving the noisy results with Enrico that I showed you at the beginning, and I did the numerics for them, I was like super intrigued in this. I was like, okay, what could this be used? And I was at the Los Alamos National Lab summer school, and this paper came out, utility for the evidence of quantum computing before evidence for the utility of quantum computing before fault tolerance. This is a kind of this paper has been too negatively kind of received, in my opinion, for different reasons. It's still a cool experiment. It was somewhat state of the art, like for actual quantum computing experiments, but it was the media kind of like oversold it, and kind of IBM corporate oversold it. The paper itself is fine in that regard, in my opinion. It doesn't oversell, at least not beyond like typical academic overselling. But then there was the other kind of criticism of like, oh, it went straight to Nature. Because if it had gone to arXiv, a lot of the like people that instantly simulated it would have just like pointed that out, and it would have like saved a lot of backlash. But still, the way I see this is that you have kind of this domain of problems, and all of and you have different methods, different classical simulation methods that cover different, parts of what you can simulate. And oops, okay, so I guess, okay, I changed those slides. Perfect. So I guess what would happen was that IBM thought they placed themselves out of this domain, somewhere, just sketching this somewhere else. But then Tensor Network simulated it. Pauli propagation from Garner Chan's group at Caltech simulated it. And we also simulated it with the surrogate version, which is like even harder than Pauli propagation, like just natively. And with the code, for example, that is already online, I guess I haven't advertised it yet, polypropagation.jl. We can get to like quantum hardware precision in like 3 seconds or something, right? So the problem is easier than they thought. They had mostly overlooked Heisenberg, and they had mostly Heisenberg picture propagation, and they had also overlooked kind of like more state-of-the-art tensor networks. But basically they were doing dynamics, so like not continuous time, but kind of like this kind of like very discrete time dynamics of transfer Ising of the Ising model. And they were sweeping some local field, and they were seeing the quantum computer does something which we think makes sense, and the classical simulation fails to make that much sense. And so they trusted the quantum computer more. And it's true, compared to MPS on their heavy hex topology, this was better. We simulated also to the same precision. And another question is, okay, who's right? So since then, the scientists at the Flatiron Institute, so Joseph Tyndall, Matt Fishman, and Miles Studemeyer have simulations that they say are converged, and they're actually mostly just a tiny bit more kind of like higher in this middle portion. So yes, our simulations last year also weren't converged, but they were definitely better than the quantum computer. And yeah, so because we did this extra work to build this classical surrogate and this extra stuff, because we have done this initial work, we can do much more with it, right? Like we can do a lot of fast reevaluations, which just go away, which would be completely out of range if you just did naive recomputation every time. Even if that was kind of fast, these kind of gives, I don't know, it's just funny. Okay, so where does this leave us? And with this, I guess, some closings. Well, with Pauli propagation, we can simulate expectation values. Right now, we could technically do sampling or some other funky stuff, but right now we do expectation values. Definitely of near Clifford circuits, we have guarantees on that. Of noisy circuits, we have guarantees on that. Kind of generic noise-free, like random-ish circuits, we have guarantees on that. But again, mostly on average, apart from the near Clifford part. There we have also like worst-case guarantees. It always works better in practice than in theory. And like on average, by insane amounts, and in worst case, still very significantly, like the make or break between it will work or it won't work, irrespective of like what the technical scaling is, right? But we're working on much more. So what is necessary for something to be hard classically? Probably, I'm saying this like a bit biased kind of from the Pauli propagation perspective. I mean, yeah, this will be biased from the Pauli propagation perspective. Basically, like no noise or very low noise, right? Because we always scale. So even on average, we scale exponentially with like an inverse of noise. Although in practice, it might work better. We structured circuit with correlated angles. For example, in quantum simulation, where you have a lot of this coordinated backflow from high weight to low weight. This is what this tends to kind of like create. Their weight truncation really needs to be cranked up, and then it just becomes really hard. If you have complicated measurements, so ones that are not just like expectation values of permission observables, we don't know how to do that. I guess you could always go to stabilizer simulation, you do something on the state and get like some entropies there. That's possible, I guess, but I haven't worked too much with that. Quantum initial states, where even if everything is simple, and you probably want that, if you just have your state quantumly, there's no way around using a quantum device. Like if you want quantum devices to be successful, I guess this isn't like an ingredient. And sampling is hard. Like sampling, as far as we can tell, is just hard. And I guess this isn't surprising with recent news coming from Google. Of course, the I don't know, like how many trillion, quadrillion years they're stating, these numbers are probably wrong, but we just don't care enough to bring the exponent down by like 10%, and because who cares about random circuit sampling really? It's interesting to see that quantum computers, I guess, can do it, right? But if your interesting application requires sampling, that's going to make it harder for classical methods. Here's a couple of papers that I've mentioned throughout, and this is the GitHub link to the Pauli propagation library. It's not yet officially released. I was hoping to do this before Christmas. I don't think it's going to happen today, but the code generally works. And it's definitely going to improve a lot in the next month or two, and you can already do everything that I've just showed you in the slides on your laptop. So yeah, happy to take any questions.
Right. Yeah, thank you very much for a very nice informative talk. Yeah, so hopefully we have some people waiting to ask questions. So feel free to just unmute yourself to ask them now.
Yeah, I have a very how to say, conceptual questions. I normally I was doing mostly quantum chemistry problem. Yeah, and although I know most of people in my area is shifting to quantum signal value transformation, this type of method, but I still think here I just want to ask a concept problem is that now because we know some parameters is classical simulable, but we also know that quantum chemistry ground state is in general classical hard. So can we use
I would say, right? I mean,
yeah, so if you do during the conversion, do you think I have a classical counterpart, like the classical circuit of my quantum counterpart, and I using this classical circuit to search the this non-well approximate region, and using this non-well approximate region as the initial state can provide a good initial for quantum to at least start from better initial that is out of classical simulable region.
Yeah, sure. I mean, conceptually, this is absolutely possible, right? It's absolutely possible that I guess I would say it should always be possible to improve a little bit with the quantum computer. I mean, given enough low enough short noise and low enough error on the quantum computer, of course. But conceptually, yes. Of course, the closer you get to the solution, the less you're suffering from barren plateaus, and then you can say, look, a quantum computer can have a more expressive parameterized model running on it, and so technically we should be able to get a bit lower. I mean, I have a couple of works on that. That's conceptually absolutely possible.
Yeah.
Because there's a couple of caveats on both sides, where yes, these things are complexity wise, they're known to be hard classically, but they're also known to be hard quantumly. So I guess it all boils down to practical, practical improvements. And there I would say, of course, if you think a certain quantum circuit should be the right ansatz to lower your energy sufficiently, but you can't classically get any further, maybe you probably can get further quantumly, but right? Absolutely. I would hope to go towards this kind of future where we have quantum computers as kind of this specialized hardware that just does the extra bit. But this also requires classical simulation to be very close, conceptually close to how the quantum computer does it. For example, how do you put a DFT simulation onto a quantum computer, right?
I think
right?
now people are doing that with first quantized. So basically, they write in that in second quantized formalism.
So for example, neural quantum states are very good at finding ground states comparatively to other models, to other methods, but they are so far from how a quantum computer functions that like how do you put those solutions over, right? So I think this kind of like hybridization, which I think would be amazing to have, right? That would just be the future, kind of like scientific future we would like to have. It really requires that the classical method itself is already quantum inspired enough so that you can just put the quantum on top afterwards and not have to pay another exponential cost to map it over to quantum computer. But I would say scaling wise, we are not convinced that there's like any exponential scaling improvement. Like we don't think this will happen. At least this is not what the formulas indicate at all. But practically, right, like, of course, anything can happen. Like practically, it could just be a world of a difference because even slashed exponents is invaluable, right?
I agree your opinion, and I also think that like all this work I think I read most of them, so I think this is inspiring for doing chemistry research. Especially I will try to look into this hybrid method to see if this like Pauli propagation can provide some better subspace. There's I know it's already barren plateaus, then I can shift it maybe to gradient-free method like Bayesian optimization, start from those subspace. Yeah.
Because you're mentioning this, so barren plateaus, yes, they are kind of originally have been defined by exponentially decaying gradients, but gradient-free methods will not work any better.
Oh.
So great. So because in quantum expectation landscapes, you exponentially decaying gradient sizes on average actually exactly correlates. Like it's one-to-one. Kind of, this is like an if and only if kind of thing. It also means that the entire loss landscape becomes concentrated around a certain mean expectation, and only very rarely do you have like kind of like significant kind of like outbursts from the concentrated mean landscape. So it doesn't matter whether it's a gradient free or gradient based. That doesn't resolve barren plateaus at all. Like practically once you all these I really like the chemistry Ansätze. The reason is that they are problem informed, right? Like all the like unitary cluster Ansätze, UCCSD, they have a lot of they have an ansatz that's like tailored to the problem, like with single double excitations kind of like built in as as your gates. And this is already so far removed from the generic circuit that I've talked about kind of in this talk, that already natively I think it's way more promising. Now the precision you need for quantum chemistry is another kind of like problem in my mind, but people like practitioners know this, of course, where yes, even if you could do classically better than classical, can you do as well as you need to for precise quantum chemistry predictions? But I'm not the person to talk to you about that caveat too much. So
thank you
yeah, thanks for your comment and question.
All right. So anyone else can ask again?
Very good. Just to let you know, you can reach out to me on like via email, for example. That's manuel.rudolph@epfl.ch currently. So like the EPFL email and then first name, last name. Or if you're on any Slack where I am, like I guess I'm on the Julia Slack, I'm on the Qiskit Slack, I'm on the Quantum Open Source Foundation Slack. So if you want to reach out for questions or comments or criticisms, just let me know. Cool.
Right. Okay. I don't know if anyone else was wanting to ask any questions. I was actually just curious about something. So when you were mentioning something about this, I think it was like polynomial subspace. Is that right?
Mhm.
Yeah. So, uh, so when you mention that, do you mean that because you would need to actually identify the subspaces, right? Like you have to be able to find them. So they are
Yes.
efficient to find.
No. So maybe I was a bit imprecise. So it's not that barren plateau freeness implies classical simulability. It's that provable. We suspect provable like freeness, like provable absence of barren plateaus implies classical simulability. Provable means you already found the polynomial subspace. It was you writing
Ah.
it down in the appendix of your paper, right?
Okay.
And a lot of works have done that in the last couple of years, like last 4 or 5 years.
But on this, I mean, isn't there additional complications that arise? It's not enough to just find the subspace, but you need to be able to take certain inner products, or there's operations that you need to do. Usually the examples we have of these subspaces, everything's like Pauli's or something really nice, but that's not necessarily the case generically, right?
That's true. I'm not aware of proofs that work in more exotic subspaces. So I mean, one clear counterexample of, well, okay, potential counterexample of this kind of like hypothesis is, um, again, if you look at like real time evolution circuits, and which probably have some symmetries, because that's, you're doing quantum simulation, and then you're doing it on average over like your dt or something, right? Like you view like your dt or your coefficients in the Hamiltonian as variation parameters, and right, but let's just say the dt, and then you can say you have one parameter that goes into every gate, right? And numerically, this has been shown in a couple of papers. These things have like large variance, right? Even super deep circuits. So it's something about physicists writing down physics problems of interest and designing the circuit, trautorization to simulate certain outcomes. And somehow that doesn't have barren plateaus if you allow yourself to think of dt as the variation parameter. But then it's not proven that this doesn't have. I don't think there's a single proof that shows this. And I think what's actually happening is that this is not a polynomial subspace. It's like a piecewise polynomial one. Like for every like time step you do, you have a different polynomial subspace. Globally, it's exponential, but it's basically like chaining together and calculating the transformations from one polynomial subspace to another one. There's probably some other like slightly different symmetric bases. Like we don't know how to compute that. Absolutely, that was like how I would interpret your question. Even if it's like piecewise polynomial, you have to do the basis transformation. I don't know how to do that. It's just that I haven't seen this actually be proven, or like things like these be proven, and be used as a solution, as a resolution for barren plateaus. I wouldn't be shocked. I mean, honestly, in the next couple of years, I definitely expect there to be progress in this direction, where there will be like more than just discrete logarithm counterexamples to the claim. But like we don't want to be right, in the sense that the people on this work are quantum computing scientists. We don't stand to benefit from being correct here, in the sense that, right, like if quantum computing doesn't do anything, we're all kind of sad. So we would hope that there's more and more physical understanding kind of going into quantum computing architectures and like approaches, and we all hope that eventually something works significantly better than classically. Do you have a specific example in mind, like where this would, some basis that is maybe you can write down, but like is practically impossible to work with?
No, I mean I've worked on classical simulation stuff, so I guess I'm familiar with a number of techniques on how to classically simulate things. But I remember, and machine learning is kind of fairly new to me, but I've seen these arguments about the subspace being classically simulable. I mean, I think the onus is on those papers to prove rigorously that these subspaces are always classically simulable, and there isn't a rigorous proof. And when you look at it, one can imagine situations where this might be hard to do because, I mean, classical simulation, there are lots of things have to work right for you to actually simulate the thing, right? I mean, if you wanted to write a rigorous theorem saying it's efficient to classically simulate this thing, then all these things have to work right. And it's, maybe I just am not familiar enough with the literature, but my understanding is things are kind of a hand-wavy statement that, look, the space is polynomial, in principle, we can track it. The examples we look at, the objects can be tracked through this polynomial space in the few simple examples we have of this phenomenon. But it's not a rigorous statement that every time this phenomenon arises. Like, I mean, every time you have a proof that there is no barren plateaus, it's classically simulable, right? I mean, there's kind of no proof of that.
So far, yes. I mean, so far, yes. And for us, it's hard to imagine how it couldn't be so. But of course, so I personally stopped caring about polynomial runtime because it will not happen. Like, nothing of interest is polynomial runtime. But we can, but this has been computational methods forever. Nothing is like, everything is hard, and it's just up to people to have new innovations, to have better understanding of what they're doing, to just make it practically happen, right? The best examples of this that I know are like traveling salesmen on like Euclidean space, where all of these continuous relaxations just give you instant solving of like 1,000 like node size problems, like exact, provably exact. But then you make it 10,000, 100,000, it's still exponential. It's just like so much understanding was poured into the solver to get the constants down, to get the exponent down. So this is personally what I'm most interested in. But I agree with you that there's absolutely, there is the chance that just because you can write down the subspace, maybe the elementary operations in that space are just practically so like no one knows how to do it. So that is possible. Yeah, I would be curious to see something like this. But I personally also don't. Yeah, again, like nothing of interest to me is polynomial. So I'm personally looking to find, just practically better simulation because of more understanding and pouring that into the classical simulation to make it just practically possible to push certain boundaries.
Sorry. Thank you for the nice talk. I just have a naive question. So what I'm wondering, in your Pauli propagation algorithm, you need to truncate at some point, right? From the end to, so you need to track all of the steps carefully. Then for your truncation, how do you like determine the truncation? Do you need to determine see the circuit structure or the noise model that can help you to have a better truncation in your algorithm? Or yeah.
So yeah, I would say the way that we choose truncations right now, at least that I choose truncations, is kind of by trial and error in a way. So this is not the answers the theorists would say. Like what they would say is, look, we have a truncation which provably works for a certain type of circuit, but then you might trunk. So for example, for noisy circuits, the most popular truncation method that gives you also the tightest bounds is so-called path weight. Path weight is kind of the sum of Pauli weights, kind of at each gate, kind of like at each each step in the circuit simulation. And because the bigger the path weight, like the sum of your individual weights, the more noise you will have accumulated. That's a much tighter kind of predictor of like being small coefficient than current weight. But I would say, well, just truncate on small coefficients. But it's hard to show, like it's hard to prove something about that, right? So practically, a lot of the, so practically everything apart from the weight truncation paper we had for noise-free circuits, all of the other truncations, as far as I know, right, are just proxies for having small coefficients. And then you can like analytically count paths, like how many paths could have this certain kind of like property, and you can make runtime guarantees. If you're in practice, just truncate small coefficients. Okay, and then there's the Pauli weight, which is kind of somewhat arbitrary, like just like knob to turn. But practically, I don't know. I don't know anything that's significantly more sophisticated than just truncating small coefficients and truncating high weight Paulis, and then figuring out what for you is small coefficient and what for you is high weight Pauli. So one thing we are working towards, and I think the field has made some progress, is incorporating certain symmetries. So this is something that you can, if you know your circuit, you know, like you can decide, oh, this is a circuit that allows for a certain new kind of propagation. Even it's not necessarily a truncation, but it's like you can kind of symmetrize, work in a symmetrized space that isn't just Pauli basis, or you do some additional merging of Paulis that, you know, are technically not identical, but up to the symmetry they are. So you can probably play a lot of tricks in this regard, like and reduce runtime. But this isn't, yeah, this would be like a new simulation approach based on knowledge of the circuit rather than truncation based on knowledge of the circuit. But but just to reiterate, if you ask theorists this, they will say, oh, all these different truncations in the different papers, you know, you would use them. I would just say, no, you just truncate on small coefficients because the papers are just theory and just proxy for small coefficient. So
Yeah.
I would love more sophisticated truncations. Let me know if you have any ideas that maybe I can, maybe I can tell you, oh, this, I think this is already kind of encapsulated, or, you know, maybe you have some really cool new insight.
Okay, thank you. So basically, it's kind of a practical approach. Numerically, you just truncate more coefficients as much you have. But so a follow-up question is that, so to say that they are classically simulable, so we are claim them at the level of like a demonstration or at the level of like a more robust claiming they can be classical simulable, because truncation matters, right? So I'm just curious, what's the level for the claiming?
So classically simulable is definitely the theoretical statement, right? It's a theoretical statement about the you know, like the ensemble of quantum circuits, or like the ensemble of input states given this type of error model, and, you know, like maybe some average case statement, and then you can count paths given your truncation scheme, how many will satisfy the precision you want. That's definitely like just a theoretical statement. Practically, numerically, I don't even I don't even know what exponential scaling really means, apart from the obvious, look, if I make my circuit deeper, it's going to be harder, because we're just looking for things that are hard at this point. But what we should be doing is look at things we want to solve, right? And these are very concrete problems. And what is scaling for a concrete problem? Like, I don't know, right? But what I would say is, even if it's technically exponential scaling, practically it's so much better than the theory suggests, that you can simulate things that every theory would say you have completely unbounded error, but you can simulate them to some, like, you know, like kind of like visual match kind of precision, and with pretty generic truncations even. So yeah, this is definitely a theoretical statement. Practically, it's probably way better. Even exponential things are much more doable than one might think.
Okay. Okay. Thank you very much. Thanks.